Acoustics are a rising concern in today's living and working environments. As function mixes and open or hybrid use of spaces are happening more frequently, it's important to find highly customizable solutions with little impact to the environment to target specific frequencies of noise nuisance.
In this project, we developed a digital workflow where designers, architects, engineers can actually craft acoustics and develop components that are optimized for acoustic performance.
The resulting design are then produced by means of additive manufacturing. We use additive manufacturing because of its potential to produce a large variety of complex shapes. It gives a lot of freedom in the complexity of the geometry, but also it allows producing pieces which are unique, meaning not necessarily based on industrial repetition.
The acoustic principle we are using is based on quarter wavelength tubes, and they absorb sound via so-called viscothermal damping. Inside the tube, a standing wave emerges, and that standing wave determines the frequency where sound absorption appears. The length of the tube and the radius of the tube both determine that specific frequency. Well, we can also achieve broadband sound absorption by including different kinds of tubes, so with different length and radius, in one product.
The computational optimization required a mathematical model. For this model, we used formulas from literature, which were anyhow not enough. Those formulas contain a specific absorption coefficient, which we derived and validated for a large set of measurements. Those were specifically fine-tuned for the case of 3D printing, which wasn't explored before.
Simulations, of course, are not enough, so we also had to do a lot of measurements. Typically, measurements are done in a reverberation room.
It's a huge room full of reflections, and by measuring in this room our sound absorbers, we are able to calculate their acoustic performance. The results are really promising, especially when it comes to lower frequencies. And we are really hoping that we will be able very soon to launch a ready product that can enter the construction industry market.
This project has really brought researchers and end users together and has really come a long way in the prototyping that it has achieved. Exactly what we need as NWR.
For Materialize, this project is an excellent illustration of the good use of 3D printing. We had acoustic experts translating a real acoustic problem into a complex geometry that can only be produced with 3D printing.
The value of the project is that it can fulfill the requirements for specific sound absorption in also a very specific aesthetical shape.
There's so much development in modern materials, so that's what has happened here, I think.
The additive manufacturing solutions to achieve passive destructive interference, together with the software tool developed as well in this project, will not only find these solutions in a very customizable way, it will also do so with less use of materials, with no use of energy, to achieve comfortable and livable environments.